Okay, well, hopefully if you plug this in, this expression in for y, and this expression in for y prime. If you did, then your y prime equals ay becomes lambda e to the lambda tx, which is what your y prime is, and ae to the lambda tx. Okay, now, we want to get this down to this form. That was a question. Yeah, show that this equation is equivalent to this equation. And there are a couple of things that you might not see immediately. Again, it's been a while since you've done matrix stuff, and you might be still a little fuzzy on it, meaning you probably should practice it a little more. But in this process, you'll get plenty of practice. Okay. The two things that we got to see to get this down to this form are that, first place, we can factor out e to the lambda t here. Okay, and I said why. It's because e to the lambda t is going to be a factor of each component of x. When you multiply a by that resulting vector, e to the lambda t is going to be a component, a linear component of every term that comes out of the multiplication by the matrix, and that's something you need to verify. But that means that the e to the lambda t can be factored out of this matrix, giving you e to the lambda t times just a times x. So that's a property of matrix multiplication. You can factor out this e to the lambda t, but there's a reason for it, and you might want to think about that. The other thing that would never occur to anybody in their right mind is that x is the same as ix. I being now our identity matrix, which I kind of warned you about earlier. Okay? Because the identity matrix multiplied by any matrix compatible with it, and this x is a matrix, it's a column matrix, and we call it a vector. But when we multiply the identity by this x column, assuming we have the right identity, the identity whose length is equal to the length of x, in this case, the identity matrix for a 2 by 2 matrix, the 2 by 2 identity matrix, so we can multiply by a column of length 2. So this is identical to this, but it seems pointless to write this. And in most contexts it would be, but in this context it becomes important. Okay, so now we have this equation, and we're trying to get to here. Now you really should pause and see if you can get from here to here without seeing the rest of it, because once you've written this out, it's pretty straightforward. So hopefully you've paused and done that, but I'm going to go on. I can then subtract this from both sides, leaving me the zero vector over here, not the zero number, the zero vector, because everything we have over here is a vector of the column vector of length 2. This had better be a column vector of length 2. It better be the zero vector for a two-dimensional column vector. Okay. So we get this, and that's really straightforward. Algebraically, it looks right. The algebra just plain old works if you're careful about making this the zero vector. And now if we do this, what do you see? Well, the algebra step that you would take if you have this is really obvious. You would want to divide by e to the lambda t because it's common to both terms. So we would divide by e to the lambda t. And we also want a to have the positive and the lambda I to have the negative. Well, the a's from here and this one's negative, and the ix is here and it's positive. So I'm going to divide, I could divide by e to the lambda t and then multiply by -1. I'm just going to say divide by negative e to the lambda t, the negative being so that this comes out in the same order as this. One way or another, you would do that. Okay, if there's just an algebra equation, you'd know to do that. And you want to justify all the steps of your algebra, but that's the way it works out. So you get ax minus lambda ix equals 0. And now we can factor out the x. Now one thing that some people did, and you really need to be careful about this, and of course your linear algebra might be a little rusty, but it shouldn't be as rusty as it was after the assignment was due today. But I understand that it might be. People would put the x here. So it'd be x times a minus lambda I. In the first place, x times a minus lambda I is not even compatible. This is 2 by 2. Each of these is a 2 by 2 matrix. This is a, what, 2 by 1 matrix. It doesn't have rows of length 2, so you can't multiply the length 2 columns of this matrix. Also, matrix multiplication is not commutative, so you should never reverse the order of a matrix multiplication unless you are sure that that particular matrix multiplication is commutative. And of course, these are things you would have learned very early in your linear algebra course, and if you're as a typical student, those would be the first things you'd forget if you don't use them for 18 months, and it's been 18 months since you learned that. Okay, anyhow, and for most of you it's been 18 months. Okay, anyhow, you can do this, and you want to be careful about the commutativity and compatibility of matrix multiplication. Now, having done this, we've got this. Now, the next question is, how does this then come down to the need for the determinant of a minus lambda I to be 0? And this is not a 0 vector because the determinant is just a number. This is a 0 number. So why would it be necessary that the determinant of this be 0? That this matrix be singular? Well, fairly easy if we think about it. What if this matrix was invertible, was non-singular? What if its determinant was non-zero? Well, again, if the determinant isn't 0, then the matrix is invertible, isn't it? It's non-singular. And you want to reacquaint yourself with those terminologies. Okay? If this matrix is non-singular, then you can invert it. Determinant's not 0, it can be inverted. So if this is invertible, then the solution to this equation would be x equals inverse matrix applied to both sides, leaves you x on this side and x and the inverse matrix multiplied by the 0 vector on this side. Well, if you multiply any matrix by the 0 vector, assuming you have the compatible 0 vector, and you would here, if you multiply any matrix by the 0 vector, you get x equals 0. And if x equals 0, then our assumed solution, e to the lambda t times x, that means x1 and x2 would both be 0. It means that your y vector would be 0. Well, that doesn't tell us a darn thing that we didn't already know. If y1 and y2 are both 0, then their derivatives are both 0, and both of these equations are satisfied, but that's totally uninteresting. We knew that before we wrote them down. So finding out that your solution vector is the 0 vector is uninformative. It's worthless. So I say it this way: if x is the 0 vector, then we have only the worthless, trivial solution. Okay? So that's no help at all. If we want to get an x vector so that we don't get a 0 over here, then this matrix had better not be invertible, right? So a minus lambda I had better be singular, i.e. non-invertible, i.e. determinant 0. So there's our condition. We assume that y equals e to the lambda t times some constant x1, x2 column vector. And we conclude that we expect to get a solution for x1, x2, provided the determinant is non-zero, is 0. So if the determinant is 0, we plug in the value of lambda that makes the determinant 0, and we plug that into our equation. Well, you'll see how that works out. And we get a solution for our x1, x2 vector, and that's the next step. So we'll do that next.